Hey guys, welcome to a new machine learning from scratch tutorial. Today we are going to implement the linear discriminant analysis algorithm, or short LDA, using only Python and NumPy. LDA is a dimensionality reduction technique and a popular pre-processing step in machine learning pipelines. LDA is similar to the PCA technique that I already showed in a previous tutorial. The approach and the implementation of PCA and LDA have a lot in common, so I highly recommend that you watch this video first. And now let's talk quickly about the concept of LDA before we jump to the code. So the goal, as I already said, is feature reduction. So we want to project our data sets onto a lower dimensional space and find a good class separation. So here we have the difference between PCA and LDA. So in PCA, or principal component analysis, we want to find new axes onto which we project our data such that we maximize the variance on the new axis. And now in LDA, the big difference is that we know the feature labels. So this is a supervised technique. And here we want to find new axes such that the class separation is maximized. So if we have a look at this image here, we have two different classes, and then we could project our data either onto the y-axis or onto the x-axis. And now in this case, the y-axis would not be a good choice, but the x-axis is a good choice because here we still have a good class separation. So this is the concept of the LDA. And here I listed the differences again between PCA and LDA. So in PCA, again, we want to find the component axes that maximize the variance of our data. And in LDA, we want to do this too. So within one class, within the green field and within the blue field, we still want to have a good variance between the single features. But also additionally, here we are interested in the axes that maximize the separation between multiple classes. So this difference here basically should be maximized in the new axis. And yeah, LDA is supervised learning, so we know our labels, and PCA is unsupervised. So this is an important thing that we should remember. And now let's jump to the math. Here we have the so-called scatter matrix, and we have two different scatter matrices, the within class scatter and the between class scatter. This basically represents what I was talking about here. So the within class scatter makes sure that our features within one class are good separated, and the between class scatter makes sure that the two or all the classes are good separated. And if we translate this to the math, then we have to deal with the mean values and the variances. So the formula of the within class scatter is the sum over the scatters, and each scatter of one class is the sum over, and then the feature value minus the mean value of all the features only in this class, and then times the same transposed, and then we sum over all the features in this class. So this is basically the same as in the PCA algorithm, where we want to compute the covariance matrix. So this is almost the same formula as for the covariance matrix, except that we don't have the scaling at the beginning. So this is the within class scatter, and then the between class scatter. Here the formula is the sum over all the classes, and then for each class we have the number of features in this class, the number of labels in this class, and then times the mean value. So this x bar is the mean value of the features in this class minus the mean value in total. So the total mean of all features, and then times the same transposed. So these are the two matrices that we have to compute, and then we calculate the inverse of the within class scatter and multiply that with the between class scatter. And this is our eigenvalue and eigenvector problem that we have to solve. So this is the same as in the PCA. I will not go into detail again, so please make sure that you know what eigenvalues and eigenvectors are. So basically what we have to do then is, for this formula, we have to calculate the eigenvalues. And then, so let's have a look at the whole approach again here. So here I summarize it. So first we want to calculate the between class scatter and the within class scatter. Then here we calculate the inverse of the within class scatter and multiply it with the between class scatter. Then of this, we calculate the eigenvectors and eigenvalues. Then we sort the eigenvectors according to their eigenvalues in decreasing order. And then we choose only the first k eigenvectors that we specified, so only the k dimensions that we want to keep. And these eigenvectors are called the linear discriminants. That's why it has this name. And then we transform our original data points onto this k dimensions. And this transformation is basically just a projection with the dot products. So this whole approach is the same as in the PCA algorithm, except that we have to solve the eigenvalue and eigenvector problem for a different formula in the beginning. So that's the approach, and now let's jump to the code. So of course we import NumPy as NP, and then we define our class, and let's call this LDA. And here we define our init, which has self, and it also gets the number of components that we want to keep. And here we simply store that, so we say self n components equals n components. And we also create a variable that we call self.linear discriminants, and this is none in the beginning. And here we want to store the eigenvectors that we compute, and then we define our fit method. So here we have self, and then we have x, and we also have y, because remember this is a supervised technique. And then we also implement not the predict method, but we call it transform. So transform. This is the same as in the PCA. And here we want to get the new features that we want to project. So let's implement the fit method. So here first what we want to get is the number of features, and we get this by saying x.shape and then the index 1. So index 0 is the number of samples, and here we only want to have the number of features. Then we also want to get all the different class labels. So let's call this class labels, and this is equal to NumPy, and then we can apply the unique function of y. So this will only return the unique values in our labels as a list. And now we want to calculate the two scatter matrices. So S underscore W for the within class scatter and S underscore B for the between class. So let's do this. And first of all, I want to calculate the mean of all our samples, because we need this later for one of the formulas. So we say mean over all equals NumPy dot mean of x, and then along the axis 0. And then let's initialize our two matrices. So we say SW or S underscore W equals NumPy 0. So we want to fill this with zeros, and we want to give this a size of the number of features times the number of features. And the same thing with the between class. scatter. So we initialize this with zeros. So later we want to test this, for example, with the features of the iris data set. So this has a size of, this has, I think it's 150 samples and 4 features. So this has size 4 times 4, and this is the same, 4 times 4. And now we have to apply the 2 formulas. So we have to sum over all the classes and then apply these 2 formulas. So we can do this in one for loop. So we say for C in class labels that we computed. And then what we want to get first is we want to get only the samples of this class. So we say x C equals x where y equals c. So where we have this label in the current iteration. And then we want to get the mean from these features, mean c equals, and this is NumPy dot mean of xc along axis 0. So the same as we are doing it here, but only for the features in this class. And then let's have a look at the within class formula. So here we have our feature and then subtract the mean value. And then this is basically the dot product times the transposed. And so let's do this. So here we say our S within plus equals, because here we sum over all the classes. So plus equals, and then here we say xc minus mean c, and then I transpose this and calculate the dot product times the same as we are doing it here. So here we have to be careful. So if we have a look at the formula again, then we see that I have the transpose term at the end, and here I transposed the first term. And this is because here we are having one more sum. So we do this for all the samples in this class. And here we do this sum in one operation with the dot product, so with our NumPy operation. And then we have to be careful with the sizes. So what we want at the end again is a 4 times 4 matrix, like here, because we append this to these matrices. And in the beginning, our xc and our mean c has the size number of samples in this class times 4. So we have to turn this around. So we have to say this is size 4 times number of samples in this class. Because when we multiply this, or when we compute the dot product with this one here, which is not transposed, so here we have the number of samples in this class times 4, and then if we multiply this, then we get a matrix of the size 4 times 4. So these are basic rules of matrix operations. Be sure that you understand this. So the last dimension of the first matrix must match the first dimension of the second matrix, and then the final output size is composed of these 2 sizes. So this is why we have to transpose the first term here. So this might be a little bit confusing. Make sure to double check this for yourself. And then we have the within class scatter. And now for the between class scatter, what we want to get is the number of samples in this class. So we get this nc by saying this is equal to xc dot shape. And here we want to have the index 0 because we want to have the number of samples. And then here again, we have to be careful because we have to reshape our vector. So let's say our mean diff. Let's have a look at the formula again. Here we calculate the mean of this class minus the total mean. So let's do this. So this is, let's say, we have the mean of this class minus the mean overall. And this is only one-dimensional, but we want to, so this is, if we have a look at the shape, then this would say 4, nothing, but we want to have it to be 4 by 1. So we have to say reshape and then the number of features times or by 1. And this is because, again, if we have a look at the final multiplication, so the same way as we are doing it here, we want to have a matrix of size 4 by 1 and multiply it with a matrix of 1 by 4. So this is basically 4 by 1 transposed. And then we get a 4 by 4 output. So this is why we have to apply the reshape here. And then we say SB plus equals, and then here we have the number of samples in this class times, and here we have the mean diff dot the mean diff transposed. And these are both of our matrices. So we finally have the matrices now. And now, as I said, we have to get the inverse of the within class scatter and then multiply it with the between class scatter. So we get the inverse also with NumPy by saying NumPy lin alg dot inf of SW. And then dot, we multiply it with the between class scatter. And let's call this A and store this in this matrix. And then for this, we have to solve the eigenvalue and eigenvector problem. So we have to calculate the eigenvalues and eigenvectors. And now the following code is exactly the same as in the PCA algorithm. So please check that. So we get the eigenvalues and the eigenvectors by saying this is NumPy lin alg dot eig of A. And then we sort the eigenvectors and the eigenvalues. And for this, the same as we are doing it in the PCA algorithm. So we transpose the eigenvectors by saying eigenvectors equals eigenvectors dot t. So this makes the calculation easier. And then we sort the eigenvalues. So we say indices equals NumPy dot argsort of, and here we say the eigenvalues, and to make it a little bit nicer, we actually want the absolute value of the eigenvalues. And then we want to sort this in decreasing order, so we use list slicing and use this little trick from start to end with a step of -1. So this will turn the indices around, and then we have it in decreasing order. So now let's get our eigenvalues in decreasing order by saying eigenvalues equals eigenvalues of these indices, and the same with the eigenvectors. So eigenvectors equals eigenvectors of these indices. And then we want to store only the first n eigenvectors, and we store this in our linear discriminants that we have here. So we say self dot linear discriminants equals eigenvectors, and then from the start, so the biggest eigenvector with the biggest or the highest eigenvalue, and then to self dot number of components that we specified. So this is the number of dimensions that we keep. And now we are finally done with the fit method. So this is the whole fit method. And then in the transform, the only thing that we do here is we project our data onto this new components. And the transformation is nothing else than the dot product. So we can write this in one line and return NumPy dot. And then we project our data onto the self dot linear discriminants. And since we are transposing it here, we have to transpose it again here. And then we are done. So this is again the same as in the PCA. Please double check this for yourself. And now we are done, and now we can run the script. So here I have a little test script, and this is basically the same as in the PCA tests. The only thing that I exchanged here is instead of PCA, we create the LDA and want to keep two components, and then we call the fit and the transform. And we do this for the iris data set. And then I plot the new labels that are projected onto the new 2 dimensions. So let's run this. So let's say Python LDA underscore tests.py and hope that everything's working. And yeah, so here we see our transposed features in only 2 dimensions now, and we see that the classes are very good separated. So here we have the 3 different iris classes, and we see that this is working. So our LDA feature reduction method works. And yeah, please again compare this with the PCA algorithm. And I hope you enjoyed this tutorial. If you like this, then please subscribe to the channel and see you next time. Bye.